story I want to tell you today. So the roadmap for my lecture today is going to be this metal to superconductor, which is just that, because Andre talked, gave a beautiful lecture on that. And I'm going to move toward what happens to an insulator and how does that become a superconductor. And I'll take the very simplest insulator, just a band insulator, Fermi band insulator. But there is a roadmap going forward that we have pushed, where we have started this work with Kyungmin Lee and Tamagna Hazra, who are both in the audience here, and they have a very nice poster where we have discussed what happens in a topological insulator. And so we look at a trivial to topological insulator in a Kane-Meillet model and ask what happens to such a system that has some Berry phases, what happens to superconductivity in that. So if there are young people here, they always get more excited about some of these more new topics. It's very hard to get a student excited about some of the questions I'm excited about, because they often don't have this history which brings us to these questions. They like to come at it from what is fashionable. So if that's the game you want to play, come right from the top, and there are some exciting questions there as well. But I'll stick to something a little bit simpler. Okay, so getting warmed up with some data, here what I'm showing you is data for that gap, delta. And you can ask, how does this delta change? Delta can be measured, the gap in the superconductor can be measured in a tunneling experiment. And so you can look at delta as a function of temperature, and delta decreases, finally goes to 0 at some temperature that we call Tc. So let's look at delta at, let me call this delta 0. And you can basically, delta 0 and Tc are connected by a factor of 2. So essentially the key point is the transition temperature is determined entirely by the size of the 0 temperature gap. And that is borne out by all of these materials. Even you can see hydrogen sulfide, which has a Tc of 200 Kelvin, still falls on this linear, on this line, the BCS prediction. So that's the reason this paradigm was indeed so powerful. But you start to look at some of the other newer materials like the cuprates or the iron pnictides and so on. And you see here is delta and here is Tc. So Tc is being determined, these are two independent measurements. Delta is being determined, let's say, by some tunneling measurement, and Tc can be determined by seeing where the resistivity goes to 0. So two independent measurements, and you see that now delta and Tc no longer fall on that line. There are many, many materials where the gap is much larger than Tc. Okay? So there is, you start to see a deviation from the well-known BCS theory. Okay, so you ask, okay, clearly the BCS paradigm is breaking down. What are the ways in which it can break down? So so one of the major assumptions in the BCS theory is that the coupling, this glue that is producing pairing, the strength of that coupling is much weaker than EF. So there are two scales we are looking at. So here is EF, which is proportional to Kf square. There is the some kind of a mode that one is coupling to, could be phonons or any other mode that one is coupling to. And so you have Tc is, as written there, the coupling to the mode is much weaker than EF, so that only a tiny portion of the Fermi surface is perturbed. So one question you can ask is, if the coupling gets stronger and more of this Fermi surface is getting perturbed rather than just a tiny shell, what happens then? So you're kind of perturbing this entire Fermi surface as the glue gets stronger. And so that is one reason why one might deviate from the BCS theory. The other assumption is that whatever this coupling glue is, So in this traditional case, the phonons, they are much slower than the electronic timescale. So the electronic timescales are like 1 over EF, and the glue is coming from some mode like phonons, and the glue mode is much slower. So on the other, so another reason for BCS theory to break down is if the mode gets, if EF gets smaller than the mode. And this can indeed happen when you have very low density systems. So one, here are some examples here of Fermi, different density of electrons, and you can see bismuth and strontium titanate have extremely low densities, and you see this, these three energy scales. EF is about 25 millivolts, so you can see how small it is. In aluminum, just to compare, EF is on the order of EV. So you've dropped it down by 3 orders of magnitude. The mode is still lower than EF, but comparable, and TC is also, a couple of orders smaller, but very, very small. This is a very recent result on discovery of superconductivity in bismuth. Okay, so this is sort of the second. This is just still coming from the superconductivity side, but asking under what conditions could the paradigm be breaking down. But now I want to be totally drastic and say, I don't even have a metal. I have an insulator. So I'm going to now come from the other side and say, if I have an insulator, how is this going to even achieve any property like a superconductor? So, I have no Fermi surface even to begin with. Okay, so a simple way to start with this is I take let's say a site which has 2 levels, and I'm going to be, I have 2 spins, so let me fill it up completely. So one level is completely filled, the other is empty. Now let me bring these sites closer to each other. So this will broaden into a band, a blue band and a green band. And if the tunneling is weak compared to the spacing between these levels, which I've called omega here, so these centers are separated by omega, but the widths have become of order hopping. So then you clearly see that if the hopping is weak, I have a Fermi band insulator, just 2 separated bands. The lower one is filled, upper one is empty. At this point, there's no attraction in the problem, no interaction. It's just non-interacting. Now, as I turn on the hopping between these sites, and if you're an experimentalist, you can think about, say, applying pressure, so that will enhance the hopping, enhance the hybridization between different sites. Then they broaden, and at some point, these bands overlap, giving a metal. Now on this, I'm going to add another axis, which is attraction or some interaction, and ask, how does this transition change? Okay, so the key result I want to communicate is the following, that as I do this tuning, this x-axis here is this hop, some kind of, I'm going to write down the Hamiltonian very soon, but think of it in the same model that I just showed you, same picture, of these doubly 2 levels per site and some hybridization hopping. So this is still the increasing hopping on the x-axis. Here was the Fermi insulator I showed you, and there was a metal beyond some critical hopping. But now when I have some interaction, this is the ultimate result I will go through for you in detail. But I want to give you a bird's eye view of what is going to come out so that you know where I'm heading in case I run out of time. So one thing we will show, and this is based on this paper with Yenli Lo, Mohit Randeria, Chan Chen, and Richard Scalatar. So what we show is that there's no direct way to go from this Fermi band insulator to a BCS superconductor. That's the first lesson. So any time you see a superconductor insulator transition, this is a very general result. And it works not just in this simple model, but it's really true regardless of whether you have repulsive interactions like in cuprates, giving you D-wave superconductivity. The parent insulating state, there's no way to go directly from a Fermi insulator to a BCS superconductor. It will necessarily have two bosonic phases intervening. So the Fermi insulator will have a crossover to a bosonic insulator. And the way I distinguish these two insulators is you look at the low energy excitation gap and see whether it is a charge E excitation or a charge 2E excitation. So let's go back to this picture here. Here are the two levels. They are separated by omega in the parent case. Now, as you turn on some attraction, two electrons will form a bound state, and this bound state will sit within the gap. So maybe this is useful here. So I have these two levels here, and I formed, let's say, in fact, okay. So let's say this is my valence band. My chemical potential is here. Here's the valence band where two of the holes here and two of the electrons in the conduction band. That's a valence band, that's a conduction band. This has formed a bound state. And these bound states produce these bound states within the parent gap, omega. And as the hopping is turned on, the two-particle bound state energy, which is typically at zero hopping, just twice omega, that starts decreasing, and at some point it goes below the one-particle gap. So that's the crossover from a Fermi band insulator to a bosonic insulator. So our claim is that before the system can become a superconductor, it already has the seeds of pairing in the insulator. So a bosonic gapped state has already formed in the insulator. And then this object undergoes condensation, Bose condensation, and you get a BEC superconductor. I will explain in more detail what it is. And then with further increase of hopping, it will cross over into a BCS superconductor.
Properties, multifractal, blah, 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 blah. So are you saying that this is generically just they are not able to identify this intermediate?
This is a more complicated question. Can I actually relegate it to the end? I'm not saying that. There can be another, so repulsion is Coulomb repulsion is tricky. And so I think at this point, let me just, there's also disorder in those problems, so that's why I'm going to take a step back and maybe come back to that later. I'm trying to distill out of, a lot of complexity, some very simple key ideas, and I agree it will not be applicable just about everywhere. There will be some caveats, because after all, we are doing condensed matter, so it's never always totally universal. Okay, but this is, so you get this point, then it goes into this BEC, and there are lots of discussions in the literature on BCS to BEC crossover. I'm characterizing all of these transitions and crossovers based on the excitation spectrum here. So the point here is when this bosonic insulator condenses, a gap will open up in the spectrum, and the question is, where is that gap located in momentum space? So let's again go back to this picture here. You can see that, so if, in BCS theory, as you all know, I have sort of my bands. This is my energy, this is momentum, and this is KF. And as we said, there's particle-hole mixing which generates the gap here. And at KF, because of particle-hole mixing, this is the gap that has opened up. if you look at the locus of that minimum gap, so your energy Ek is delta K square plus Ck, or let me write it as epsilon K minus mu square. So if you look at the minimum gap, that happens at the Fermi energy, and this goes to 0, so you get this, you get a gap of order delta, but the contour is situated, the minimum gap locus is situated at the Fermi wave vector, and it's a circle. What we will see, the distinction I will make between BCS and BEC is that this minimum gap locus will be at K equal to 0. So this is a point as opposed to a contour. Okay, so there is this is a crossover, so usually there is not a very sharp distinction between these two states, but using the excitation spectrum, we can actually find a sharp way of distinguishing these two from the locus of the minimum gap, which is a point here, and it will be a full contour in the BCS state. Oh. It's this kind of a, I'm going to write the Hamiltonian right now, but it's like this, the hopping or the bandwidth is being shrunk as you go, is being increased as you go toward the right. Okay, so as I showed here, that as the bandwidth is increased, right, as the hopping is increased, you go from a band insulator to a metal, and now if I turn on attraction, then the same axis shows that now you have these two intervening bosonic states.
Can I ask a question?
Yeah, yeah.
Very quickly. This transformation from contour to a point is where chemical potential goes to 0.
Yeah, goes
chemical
negative.
Potential generally is a function of temperature. So does it mean that it's not a sharp crossover line, it's a function, it's a line which by itself depends on temperature?
Okay, at this point, I'm just saying even at 0 temperature. So you could also be talking about these crossovers as a function of temperature, but let me even set temperature equal to 0 and then have this transition. Okay, so everybody good with this big picture thing? And it'll get clearer as I go on. Okay, so this was just to quickly show that you can have a number of, this is just to flash that there are a number of superconductors now being discussed in the literature, where you have these superconducting domes. So you go from a superconductor into some kind of insulator, and very often the discussion in the community is at a very coarse level of just saying, okay, it is a superconductor, it has become insulating, but the nature of the superconductor needs more refined discussion. Is it a BCS superconductor? Is it a BEC superconductor? What are the energy scales that are driving TC and so on? Similarly, the insulator, are there signatures of the emergent superconducting state already existing in the insulator? That's a question we should be paying attention to. Okay, so what I'm going to do is, just to make this whole thing very concrete, take a very specific model where these are the ingredients I want in the model. I want it to be translationally invariant. Disorder also is an interesting problem, but we have worked on that before, and we want to actually simplify it. So today I'll take a translationally invariant model. I need at least 2 sites per unit cell because I want 2 bands, or you can have 2 orbitals per unit cell. And I'm going to turn on attractive interactions because I want superconductivity. That's, as we heard, you can also have repulsive and discuss it in the context of cuprates. But at this point, I also want to keep this, I don't want any competing orders, because that's another thing that will complicate the analysis. I'm trying to distill really the minimal ingredients I need to address this question. Okay, so so I'm going to take a triangular lattice because that suppresses CDW order, and I will, instead of taking 2 orbitals on a site, I will just take a bilayer. So the energy scales that I have are a hopping within a layer, a hopping between layers, that's like some kind of a rung hopping, attraction, which is just on-site, attractive attraction, and a chemical potential that I'm going to fix so that I have an average density of 1 per site. So it's like the valence band is completely filled. Okay, and I'm going to take T equal to 0. T perp, which is this rung hopping, will be my unit for energy. So I'm going to now have these two axes, attraction in units of T perp and hopping in units of T perp, and I want this phase diagram. Okay. So good, everybody gets what the problem is? Okay. So maybe it's a good idea to draw this axis, because then I'll fill up. What you will see is that's another, maybe I have a picture here. Yeah. What you will see is that a problem like this cannot be solved by any one technique. And it's actually very useful to bring different techniques to bear on this problem. So you can see that if I'm at small u, then clearly you can use U as a perturbation and do diagrammatic perturbation theory. You can also do mean field theory. You can do mean field theory anywhere, but it works well in this region. Then at small hopping, this basically, and you can increase the attraction, that becomes an atomic limit. So you can get some degree of control over here. And then going at the top, when U is much bigger than, much larger than T perp. So in the strong coupling regime, essentially you get bosons. So you know, we think of Cooper pairs as bosons, but they are usually, within a Cooper pair, there are many other, the Cooper pair coherence length in typical BCS superconductors is huge. So you have many other electrons within that range, but at strong coupling, they become tightly bound Cooper pairs. And this region here can essentially be discussed in terms of a bosonic theory. And what I will show you is that the middle region is mean field theory actually does very badly. I've generally been a big supporter of mean field theory because it's so easy to do and gives you the first brush of what is to come. And typically for problems that I have used determinantal Monte Carlo, it changes things only you know, you might, for example, you may not see a transition within mean field theory, or the transition exponents may be wrong, but more or less mean field theory gives us a very good idea. Here you will see the mean field phase diagram is really completely off compared to the actual behavior, and that is brought out in the middle region here where all scales are comparable by determinantal quantum Monte Carlo. So that it's a good problem if students are trying to learn a bunch of different techniques to try to apply it to a simple Hamiltonian from many directions and see what are the strengths and weaknesses of different approaches. Okay, so maybe just keep this in mind here. This phase diagram, this is T over T perp. That's U over T perp. And you know, basically, this is the model. We have hopping on a triangular lattice, which is T, hopping between two lattices, two layers, which is T perp, and U is N up, N down, minus U. Okay, and the chemical potential is always in the middle of the band. Okay, so for the triangular lattice, what you find is that the Fermi band insulator to metal transition happens at some critical value. So that's at 0 U. And as you turn on a small u, the band insulating gap protects the Fermi band insulator, so it continues to remain an insulator. The metallic side, as we just saw here, becomes unstable to superconductivity. Now, what kind? We will come up. We'll discuss that. Okay, so the other limit we can get a handle on is going on this axis, Here you can see its atomic limit, so hopping is 0. So we are basically looking at a rung, and on a rung you can have either 0, 1, 2, 3, or 4 fermions. That's the total Hilbert space. And the ground state is just a linear superposition of these configurations, where both fermions are on one or the other site, A or B, or they are equal superposition on AB, up, down, and down, up. So that's the ground state. Okay? Now we want to look at the excited state. So I had all this prepared for a Blackboard talk, and I decided, best to do it here because it often doesn't show up on that. So let's look on the Fermi insulating side. The ground state is this one. The excited state has either 1 or 3 electrons. That's the lowest excited state. So that's why we call it a Fermi insulator, because it costs energy to add or remove a single electron. As you increase U, the bosonic nature is revealed in that the lowest excited state, now you see how these energy levels have shifted. The lowest excited state actually involves removing either both or adding 2 more electrons. So n equal to 0 or n equal to 4. And that's this transition from a Fermi insulator to a bosonic insulator. So if you just work it all out, you find this is as a function of now U over T perp. So I'm going along this axis, and you'll see that when I'm below a certain value right here, U over T perp less than this critical value, there is a gap to single particle excitations, which is lower than the gap to the pair excitations. The pair excitation is the difference between the blue and the black curve, and that costs more below this U over T less than a certain value, but above that critical value, the pair excitation becomes cheaper. And that's how you're entering the Bose insulating state. And then at some critical value, even the pair excitation, so the pair excitation gets cheaper on this axis. So this axis then has this transition from a Fermi insulator to a Bose insulator. Okay, now let's complete the rest of it. So what I'm now next calculating, so we have these 2 points, and we'd like to understand this transition from a Fermi band insulator into a superconductor better. So we want this boundary here. And a quick way to get that is by looking at the pairing instability. This is kind of a standard calculation you would do. You take a pair and at some time t equal to 0 and destroy it at a later time, and this pair susceptibility then chi of omega as a function of omega has these peaks at certain omega equal to the energy to create a pair. So that's and this is for a fixed value of u. Okay? So what you see here is that this pole essentially moves to 0 frequency. So you're looking at this divergence chi inverse of omega pair, and you want to see when it comes to 0 frequency. So that's this plot. So I'm showing 2 things here. So that's this 1 over chi, which is going to 0 exact. So the key point here is that when you are at some value of t over t perp, let's say below the transition to the superconductor, then you have a 1 over chi that diverges at a particular energy, and that energy essentially goes to 0 at the transition. Okay? This energy at which it diverges is exactly this energy for the omega pair. So another way to say it is, if I look at the energy for the pair excitation, that is a finite value within the insulating state, and it ultimately goes to 0 at some critical point, at beyond which you can now insert pairs at 0 energy, and that's the definition of a superconductor, right? In a superconductor, we have a fixed phase of the order parameter. As a result, the number of Cooper pairs is completely uncertain, and that tells us that while there is a gap to single particle excitations, there is no gap to pair excitations in a superconductor. So that's what you're seeing here. So there's a crossover from where omega pair becomes lower than the single particle excitation. That's the crossover from Fermi band insulator to Bose insulator. And when the pairing gap goes to 0, the system becomes a superconductor or a superfluid. Okay, good. Any questions here? No. Okay. Okay, now maybe I'll skip this for now, or I think I should. I don't want to tell you about too many details. That's one of the things I'm worried about. Okay, let me just summarize this. Okay, let me put all of it up. Sorry, here. Okay, so here are the different energy scales as a function of T over T perp. We discussed 1 over chi and omega pair, and I had kind of drawn the single particle gap as a constant just because I wanted to get the main idea. But the single particle gap also has some variation with T over T perp. The key point is that the single particle gap is finite all across that transition. Okay, that's the main key point. That when we talk about, let's say, a superconductor to non-superconducting transition in a BCS theory, it's always determined by the single particle gap going to 0. So here, one of the key points is that you're going from a superconductor here to an insulator, but throughout that entire region, the single particle gap remains finite. Now, it has different behaviors in different regions. In the band insulator, it's just given by, say your band gap to begin with, but then it is modified by having a finite hopping. Okay, but it's some e.g. Single particle gap. Within the BEC regime, near the superconducting transition, the single particle gap is given by e.g. 0 square plus delta square. And then in the BCS regime, the single particle gap just becomes equal to delta, but nevertheless always finite. What tells you about the transition? Some energy scales must go to 0 at the transition, and those energy scales are the pairing gap, which goes to 0 at the transition, and the other quantity is the superfluid stiffness. So the best way to understand the superfluid stiffness is once again to think of that superconductor as having a complex order parameter. So C dagger is a complex order parameter which has a magnitude, let's say delta e to the I theta, and the tunneling is essentially measuring the magnitude of the order parameter, and the stiffness refers to the following, that in the ground state of the superconductor, it has long range phase coherence, and that means that if I looked at the superconductor spatially at different points, they would all be aligned. These phases, this is my theta, it would all be aligned, so it would all be like theta equal to 0. Now, the stiffness refers to making a perturbation on the superconductor, for example, by applying a twist to the wave function. Okay, so suppose I twist the wave function in how, okay, let's say by some magnetic field or vector potential, let's not go there, but let's say I put some boundary condition which forces the phases to be along these two directions, then the system will respond. It's like spin waves. The system will respond by twisting these phases. And it will try to align, rather than just twist one of the spins or one of the phases and make it aligned, it will do it gradually, because then the cost of in energy, delta E, will go like some stiffness coefficient times the gradient of theta square. So it's the superfluid stiffness that refers to how the phases, how stiff the phases are to any changes that you make. And that superfluid stiffness is another characteristic of the superconductor. Now, just to put it in context of BCS theory, if you were looking for the superfluid stiffness within BCS theory, it's a very large energy scale. Actually, I can't even, so here is rho s, which is really on the scale of EF. This is for a traditional BCS superconductor. And delta is much, much smaller. So this is on the order of EVs, and this is on the order of millivolts. But nevertheless, in a BCS superconductor, the superfluid stiffness also crashes at the same temperature Tc. Okay? Now what you see in this calculation, the BCS region is way up here, where this is the stiffness. I've denoted it by ds. It's the same thing. But this, in 2 dimensions, in fact, the superfluid density and the superfluid stiffness, all of these have units of energy. So we can continue to talk about energy here. So in the BCS regime, the stiffness is a much larger scale compared to delta. And what you see as you come toward the insulator, the stiffness is dropping, but delta is is a larger energy scale. So one of the things that is starting to happen here is the transition temperature, which was in the BCS regime determined by the gap parameter. The transition temperature is always determined by whichever energy scale is the lowest. So in this region here, already the stiffness is lower than delta, and the Tc is now getting determined by ds. So that's why in the beginning when I showed some of the quantities were not scaling with delta, it's because the mechanism by which superconductivity is going to get destroyed in these materials is by the stiffness going to 0 rather than the gap going to 0. Okay, but you see that the BEC regime, based on how I'm going to define it, this being a crossover region, it will depend on what definitions one uses. And I'm going to use the definition of the lowest excitation contour. That may give a different point of transition between crossover between a BCS and BEC. Okay, so I'm going to run out of time here, so I'm going to say some important things at this point. So if you go through this analysis, sort of the way I have described it, and you can do mean field theory as well, which is very standard, this is the phase diagram you get. There's a Fermi band insulator, BCS superconductor, the 2 we expect, but then intervening, there are these small regions of a Bose insulator and BEC. But this phase diagram is actually wrong, because when we put in fluctuations through Monte Carlo, and this is what I said, I was kind of surprised, because usually I've seen Monte Carlo may change things, close to these transitions and so on, but this is the actual result from Monte Carlo. You see that the Bose insulator is a very large region. In fact, tuning with the band structure and tuning with attraction is a totally different scenario. So in this, if your hopping is small, you never enter a superconducting state just by tuning attraction. And so the topology is also different. And we know some of these points very well. The main message is that insulating, this particular bosonic insulating state is not captured well by mean field theory. Okay, so let me show you some evidence for this from Monte Carlo. So I'm going to take like just couple of cuts through this phase diagram. So let's take a cut through this where mean field theory had said that you are always superconducting. Either it's a BEC type or a BCS type, but it's always superconducting. So let's take a cut exactly from here and see what Monte Carlo gives. Okay, so that's the cut. Now, look on this side. We can calculate this ds, or the stiffness, by looking at a current correlation function. So the Monte Carlo here, a couple of things to talk about it. There are many different Monte Carlos that you can do. Yesterday we heard about variational Monte Carlo in the talk on spin liquids. There it's totally different. You start with a wave function and then you try to put the constraints exactly. This Monte Carlo works with path integrals in imaginary time. And then because it is attractive U, actually there is no sign problem for fermions. And this is true for any filling. So it's a very powerful technique because it has only statistical errors for this Hamiltonian and no sort of systematic errors coming from sign problems. So that's a useful method here. And when we look at this superfluid stiffness from this current correlation function, what you find is that for hoppings below a certain critical value, the superfluid stiffness is 0. So that determines that the state is indeed an insulator. And above that, it is finite. So it's not saying anything about whether it's BCS or BEC type, but whether it is superfluid or not, it can tell you that. Okay, and there is a continuous transition from one to the other. So that's how we know this boundary right here. Okay, now coming to, okay, let me skip that. Yeah.
Is it understandable from general principle why you increase U and you don't get BEC state?
Yeah. So it comes down to the phase fluctuations that become important. So once you get these bosonic, so like, you know, so actually the best place to go to is go to this limit here, strong coupling limit. Okay? So you do see that beyond some hopping, you do get a BEC state.
Right.
But below some critical point here, the hopping is not large. It's like a Mott superfluid transition, except these are sort of like rung bosons. So if you start here at t equal to 0, you have the two bosons. You basically have a rung like this. This is the A and the B site, right? And you have a Cooper pair sitting here. That's the boson. And basically, what you are getting is a Mott insulator of these rung bosons when the hopping is not large enough. Beyond some hopping, then you go from this Mott state to a superfluid state.
This is the bosonic Hubbard model.
Yeah, it's a bosonic Hubbard model, but the filling is, so because these are like hardcore bosons, so you have sort of one boson for every two sites. Yeah. You know, in this
respect, BEC state is a state which is superconductor.
Yes.
Right?
Yes.
So it's not state of preformed pairs.
What do you mean by?
Spectrum contains
okay.
delta but does not contain superconducting order, and it turns that phase is fluctuating as crazy.
Okay. Let me come to that. Yeah. So, so by BEC, I mean a superconducting state, but let's come to the excitation spectrum. Okay, so let me actually hop a bit. Okay, just to again orient everybody on this. Maybe I can even skip that. Okay, no, I need this a little bit. So I'm going to look at the excitation spectrum, right? So the spectral function of a Fermi gas, you know, I have a band which disperses in this way. If I look at the spectral function, it tells me about the probability of finding an electron at some k and omega, and that's, let's say, a delta function, which disperses in this way in a Fermi metal. Okay, now in a superconductor, because of that particle hole mixing that I mentioned, you have weight both in the below the chemical potential and above. So Vk square and Uk square, and their weights add up. So when you are far from, you know, so it's like here, at some point on this place here, it's mostly electron-like, and here it's mostly hole-like. And there's the mixing which is maximal at the chemical potential, right? That's the point. So now, the excitation spectrum looks like this. So in the BCS regime, I'm showing this band bending around this. And the key difference with the BEC regime is that the chemical potential becomes negative. So it marches as you go into the BEC regime by either tuning hopping or tuning U, the chemical potential has moved below 0, below the bottom of the band. And what that does is your contour, your minimum gap, which previously was at mu, so that's the circle, has now moved to the gamma point. So that is what I would call a BEC superconductor.
But this state still has delta. Right?
Still has delta. Oh, yeah.
If I ask,
oh, yeah.
What delta vanishes?
Oh, okay, okay.
Where is this boundary?
Okay, okay. This state still has a gap. Okay. So let me roughly go back. So I think this picture may help answer that question. Yeah, this one. So you see, here is the BEC regime. This is the BCS regime based on this minimum contour, whether it's a circle or a dot, and delta is finite in both regimes. That mod delta vanishes at SIT.
Right. And if you go back to your phase diagram, which you obtained numerically, this one, the next one.
The next one, yeah.
Yes. So if I look at mod delta, it still vanishes on
It
solid.
still vanishes on the solid line.
Okay.
Yeah. Mod delta is that order parameter magnitude. Okay. So I think again, this is the picture I should. Okay. So let's get all the gaps here. So mod delta is the order parameter magnitude, which indeed it's this C dagger expectation value, which indeed will have to vanish at.
That makes sense.
Yeah.
The actual value of it doesn't actually fall into the evidence. So it's vanishing because the phase is fluctuating. What do those numbers use?
No, let me actually back up a little bit from that. Okay, so at this point it is even mean field theory, okay, and if you look at mod delta, it will vanish. Now the single, so you may ask, does that mean the single particle gap vanished, right? And this is the point here. The single particle gap was indeed equal to delta in the superconducting state, regardless of whether it is BCS or BEC. Okay? But when you come to the insulating region, the single particle gap is not 0. It is finite. It is equal to this object here. So the single particle gap is still finite. It's just a combination of some other properties of the insulator, but it's still finite. So if you ask the question, does delta vanish? Answer is yes. Does the single particle gap vanish? Answer is no. Yeah. And okay, this aspect is still true even in the, so let's come back, okay, I will, so coming to the Monte Carlo, let's say here, so here, this says that at the transition, the superfluid density vanished. Then we also looked at this off-diagonal long-range order, which I wasn't going to talk about much, but that also vanishes at the transition.
But it doesn't measure modular delta.
Yeah, it doesn't.
Right.
Yeah,
Right.
it doesn't, but you can look at the spectrum. So you can also look at A of k and omega. So can I just take a minute to say that? So to answer the question about what is happening to the spectrum, that would measure mod delta, right? So the mod delta, I think I have some Monte Carlo results right here. So this is now on the triangular lattice. You can measure the g of k in tau, g of k as a function of tau, and from the decay you can extract the gap scale. And what you find, so this is shown here. This is now the BCS regime. It's Ek, so that's this Ek, which is delta square plus Ck square. And you see this band bending behavior going along some k direction. And this is now in the BEC side. You see that this dispersion has moved such that the minimum gap is now at the gamma point, at the k equal to 0 point.
Right, but this is change of chemical potential. Right.
Yeah.
This is not delta.
No, this is not delta, okay. So to get delta, we have to go back to the, so from the Monte Carlo, we cannot directly get delta. We can only get the correlator.
If I may,
Yeah.
When you go up vertically, say at
Yeah.
T part almost 0 in your phase diagram,
Yeah.
you have two phases. If you go back one, even here, you go up. Suppose that T is T or T part is small. You go up and you go from Fi to Bi phase. And if you look at excitation spectrum of single particle excitation spectrum in Bi phase, does it look like square root of delta square plus epsilon square? Because you create pairs.
Yeah.
You create both.
Yeah.
So can we view it as a development of a gap, which then condenses into
Yeah.
BEC state?
Right, right. So that omega pair that I described earlier is exactly the gap here. And that gap closes. So it is exactly the bosons that you created that then
Right,
condense.
But if you go horizontally,
Yeah.
then it doesn't close.
No, it still does. It still does. Yeah, in both directions. Okay. Let me, how much time do I have?
Oh, goodness, sorry. You should wrap up.
Okay. Okay.
Sorry.
I was, no, that's fine, that's fine. Let me see. I was going to show one quick example of this, of the minimum gap locus, because that may be something new. So what we want is, you know, we want to tune something. Now, attraction is not something that is usually tunable, but the bandwidth is. So this is data from Amit Kanigal's group on iron selenide, telluride, where you can play with Y and X to change some of these parameters. So let me do this quickly. The main thing you want to take away is that EF can be tuned by changing the Y concentration. Okay. So what is shown here are, it's plotted the other way. So this is the BCS side, this is the BEC side. And what is changed in this, going from the BCS side, which is more familiar, is that you have a, so this is sort of a whole band, and the bandwidth, which is you know, the distance of the bottom to the chemical potential, this value is changed as you go across. So let's see what they have from 20 millivolts to 6 millivolts. And what is, where is that? Yeah. And what you see here is that when you're on the BCS side, there is this clear band bending, opening up a gap at the chemical potential, as you see here. You know, so at KF, you're opening up a gap. But as you go toward the BEC, the gap opens at the gamma point. So this is at least a very clear experiment showing that crossover. Now, what is still missing is an entry into the insulator. So this is my, and I will kind of, okay, just one second. I'll just end with this, that at this point, we have growing evidence of BCS to BEC crossover in many, many systems, including the cuprates. And this has usually come from looking at the energy scales for delta and ρs and seeing which one is bigger. So on the BCS side, ρs should be bigger than delta. On the BEC side, it should interchange. But what is still missing are experiments going into the insulator and looking for precisely these bosonic pairs in the insulator. Sorry, yeah, Vafa.
So I presume that in this pigtide material that you're just discussing, you're looking at the gamma point only. Now, at the endpoint, at the corner of the girl unknown, the system is still metallic with, I forgot, of order 50 MeV permeability. So this is not quite a fair
Yeah.
comparison.
So So now, yeah, that's right. So it also can happen when you have multiple bands. Some bands might be in the BEC limit, some could be in the BCS limit, so it gets more complicated, yeah. So you can have like a band-dependent behavior. And then, as you also said, temperature-dependent behavior. So,
Right.
okay.
But if you calculate stiffness,
Yeah.
stiffness is a summable contribution
Yeah.
for all bands.
Yes.
So in this respect, you may have small chemical potential on one
Yeah.
of the bands.
Yeah.
But if you look at stiffness,
Yes.
it's still large.
Right.
overall stiffness.
Right. So a bottom line, I would say, what is the main message? Let me try to end with that. Main message, let me see if I can, just put up just this. So the main message is in terms of gross, macroscopic properties, there's a superconductor with, let's say, a finite stiffness. That's a very characteristic property of the superconductor, no matter which one you have. And a gap in the excitation, a gap delta. Now, one thing I didn't say, I'll just take 1 second to say that because I missed that point somehow, is that, you know, when we were talking about this delta, there is a clear signature which is different in the BCS and BEC regime. So let's just look at that. In the BCS regime, which you're all familiar with, there is a gap in the spectrum, single particle gap, and because of the flatness here, it's like a Van Hove singularity, which gives you a square root anomaly. When you go to the BEC side, the chemical potential has become negative, and so your energy basically has a step function. It has a jump discontinuity, at least in 2D. So the behavior in tunneling is very different. So these are some predictions we can make for clear measurable quantities in the BCS-BEC crossover regime in tunneling as well as in ARPES. And then the main summary for open questions I would like to say are for people to look more closely at really the insulating state. So while we can debate a lot of things about BCS-BEC and what is happening on different bands and what may be happening macroscopically, the really new thing is to look at the insulator near every superconducting dome that we have so many examples of and ask whether the insulator already has the seeds of the superconductor that is going to be born. So I think let me stop with that. Thank you.